So Attila, stage is yours.
Okay, thank you very much. And I thank also the organizers for the possibility of this talk. Today I will talk about applied quantum physics in strong field and attosecond science. Yes, my co-authors, Kristina is my current PhD student, and Szabolcs and Szilárd were my former PhD students. All of them work at Eli Alps. First, I will talk about motivation of this work. Then I will introduce the main concept of this MMA-HAG code structure. And then I will argue why we can do 1D quantum simulations instead of 3D. And then I introduce our recent, most advanced upgraded 1D soft-core Coulomb potential. Then I will show you some preliminary numerical results obtained with merging this MMA-HAG and this upgraded soft-core Coulomb potential. Maybe not all of you know what is Eli Alps. So it is mainly a user facility, but also a research institute. And this current work is a good example of how a fundamental research turns into something useful for the user community. Eli is governed by this European Research Infrastructure Consortium, and it has 3 facilities, and the Alps facility, which is at a second light path source, is situated in Szeged. Okay, the main structure of Eli is starts out, the main lab structure of Eli starts out from lasers, which usually create secondary sources, and usually these reach end stations where some interesting experiments happen, which then detected, analyzed with metrology and with auxiliary simulations. This topic, what I'm talking about today, is connected mostly to this gas high harmonic generation beamlines, which is the main instrument at Eli, which is able to give XUV radiation at very narrow energies, or if it is tuned that way, it is able to produce at a second temporal length XUV pulses. Yes, okay. What is at the heart of this high harmonic generation process? Actually, in a typical experiment, a suitably intense and short femtosecond laser pulse propagates through a noble gas sample, usually a gas jet or a gas cell in the millibar pressure range. This is an actual photo taken by the group of Ferenc Krauss roughly 20 years ago, where this is actually the gas jet illuminated by the through propagating in near-infrared pulse. And in this gas jet, this infrared pulse generates XUV radiation, high harmonics, which then can co-propagate and using specialized optics can reach other targets with varying time delay. And this enables pump probe experiments in a very broad range of parameters. So for us now, the main focus is what happens when this at a second pulse or XUV radiation is created in this gas jet. And for this, I draw this schematic drawing for this. So this is the gas jet produced by some valve, and an near-infrared pulse with intensity in the 10 to the 14 watt per centimeter square intensity range. propagates through it, and during the propagation, it creates XUV radiation, and also, of course, it also distorts, modifies itself. Okay, to model this, based on that the interaction, which is relevant for the XUV generation, is modeled by quantum physics. Our colleagues listed here developed a few years ago a supercomputer code, which was actually a concatenation of other purpose supercomputer codes. Namely, the first, we propagate this strong infrared femtosecond pulse through the medium with the usual nonlinear optics taken into account numerically. And then we have in each spatial point of the medium the temporal shape of the laser pulse, which depends, of course, on the spatial position. And on a sample grid, the grid of spatial points, we then solve the time-dependent Schrödinger equation, which is the basis of how this XUV radiation is generated. And from the solution of this TDSE, we can compute the source term for the classical wave equation for the XUV electromagnetic modes, and for the XUV propagation, linear propagation is sufficient because their intensity is much lower than for the infrared. So this is the main structure. Here we have some more details about these three constituents, but I just go through them. Maybe here I mention that this code employs this so-called soft core Coulomb potential for the quantum dynamics. And yes, now what happens actually when such a laser pulse hits a single atom? These figures were also borrowed from a famous paper of Ferenc Krauss and Visha Ivanov. The main thing is that this laser pulse induces tunnel ionization usually of a single active electron from typical noble gas atoms, and then this electron that was stripped off from the atom is driven by the laser field, and it is driven back to the atom usually. And if in lucky circumstances, this atom that was just ionized recaptures this electron, and during this excursion driven by the laser field, the electron gained a lot of kinetic energy, and when it recombines with the parent ion core, then a much higher energy photon is emitted. So this is the basic picture behind high harmonic generation. Okay, to treat this correctly, we need to solve, of course, the Schrödinger equation. This is a typical example where a 3D Schrödinger equation for a noble gas atom is solved for a very short near-infrared laser pulse. Here I listed the typical parameters, and the interesting things start to happen when the laser pulse is around its main peak. Okay. And earlier we created a specific 3D solver for the case of linear polarization. And if we, yes, I skip this. If we take a typical results of this 3D solver, it's not really well visible, but the main thing is that you have to see that the main dynamics happens along this horizontal direction, which is the direction of the laser polarization axis, which means that approximately we have a good chance that we can approximate the dynamics, the 3D dynamics with 1D dynamics. And then this would make quantum propagation much more affordable. And this is the basis that we can include it into a supercomputer code for a macroscopic medium. But for to be really to have a meaningful results, physically, quantitatively meaningful results, we have to create an optimized 1D atomic model potential for this purpose. And by this, in this research area, we mean that the 3D Schrödinger equation and the 1D Schrödinger equation should give quantitatively matching results, provided that the same electric field is used, the same laser electric field is used in both simulations, that we can avoid artificial scaling of the electric field from the real 3D situation into this model 1D situation. A few years ago, with Szilárd Bajorosi, we had actually Szilárd had a very good idea how to arrive at such a optimized 1D model potential. And the basic idea was that we start out from the 3D ground state density of our noble gas atoms. We reduce it into 1D by integrating over the perpendicular directions. And the ground state density that we arrive at this way, the 1D ground state density, then we look for a 1D potential that has the same ground state density. And if we can compute this, or we can calculate this on a paper directly, at least for hydrogen atom. And then we arrive at such a 1D model potential. And we began numerical testing of these potentials. And within a few months, it turned out that actually not this is the best, but a so-called improved soft core Coulomb potential seemed then to be a good improvement. Here I plot with green the traditional soft core Coulomb potential, and with yellow this so-called improved soft core Coulomb potential. The low frequency behavior was excellent, so the 1D and the 3D results match beautifully, but the high frequency match was actually 2 orders of magnitude off, but the structure of the high harmonic spectra were really similar, but with a large overshoot. And we were also optimistic that the spectral phase was very well matched. And that time we simply applied an artificial scaling of our 1D results. But later, with our current PhD student, Christina, we analyzed why did this improved soft core Coulomb potential overshoot in the very important high harmonic range. And we found out that actually this potential in its center binds too tightly. And thus it creates an artificially large amplitude in the high harmonic spectrum. And Christina was clever enough to correct this for this behavior. And instead of the previous modified or improved Coulomb potential, soft core Coulomb potential, now she created the red curve, which has the name, this Gaussian window soft core Coulomb potential, GSC potential. And we just proved that it really corrects what it has to correct. And now the main thing that you may see now, that the red curve is the closest to the 3D result black curve, and the other 2 curves are an order of magnitude off. So we now finally have a really optimized 1D soft core Coulomb potential as a 1D atomic model potential. The same results, not for hydrogen, but for argon. We treat all these noble gases still in the single active electron approximation. And now then we turn to this MMA HHG code and replaced the original soft core Coulomb potential with this Gaussian windowed optimized soft core atomic model potential. And now I'm just showing you preliminary, I stress preliminary results from the Commodore supercomputer, which compare the soft core Coulomb and this Gaussian windowed soft core Coulomb potential results. Here you can only see that they are not exactly the same. There are important differences. Now, this is what an experimentalist would see if we would visit him or her in the lab and would see what a spatially resolved spectrum, high harmonic spectrum would look like. Again, we compare these two atomic model potentials results on the left and on the right. Not much was seen actually in the display, but on a logarithmic scale, we see that really there are the harmonics that we want. And again, if we make a cut through the middle of this spatial region, we can compare in this figure in the most visible way the difference between these two model potentials. All these simulations results that I showed you now are not yet comparable with the experimental results, although this would be the final aim of our research, because these simulations cover only a very narrow medium, and our experimental results are almost an order of magnitude, use almost an order of magnitude longer medium. But already with these simulations, we are stretching the limits of the Commodore, both in CPU load and in the upper limit of the runtime. So we have to develop we have to modify something to be more to have more reliable and more practically important results in the near future. So this is my summary and acknowledgements, and I thank you for your attention.
Thank you, Attila. So, Tony, thanks.
If I understand correctly, this Gaussian soft core Coulomb has nothing Coulomb in it, because soft core in the middle and the Gaussian and the other side. So the question is that what is the physics behind the Gaussian damping?
We wanted a behavior that is more like the traditional soft core Coulomb in the middle, and has the asymptotics of this improved soft core, and we wanted to match them very smoothly. This is why these Gaussian window functions were applied.
But why Gaussian? So what this is a damping effect, or what is the physics behind it?
To have it very smoothly. Okay, so just try and win. Okay, thank you.